Astronomical Society, the Astronomical Society of the Pacific, the American Physical Society, and the Optical Society of America, Father Coyne has been awarded numerous degrees, honoris causa from, among other institutions, Loyola University, Marquette University, and Boston College. Further, he was awarded the Lyndon Medal, which honors pioneers in the sciences by Villanova University in September of 2008, and the George Dan Prize by the American Astronomical Society in January 2012. When Father Coyne is done with his presentation, we'll have a brief question and answer session we invite all of you to stick around for. So without further ado, please join me in welcoming Father Coyne to us Mercy into the Alpha Community Lecture Series.
Thank you, everyone. Thank you, Molly. I'm so delighted to be here. I got so excited talking to some of the students that I forgot to ask what I do up here about advancing slides and all. So bear with me. Once I get started, I'll be pretty good. So these introductions, I don't recognize myself. But I'm used to not recognizing myself. I grew up in a family of 10 children, and about 6 to 8 of us had to be to school at the same time, you know, elementary school or high school. Mom's fixing lunches and all of this. And I'd come down the stairs and she'd say, Richard, no, Mom. Vincent, no, Mom. Robert, no, Mom. Who the hell are you? My mom had German background. Okay, let's get more serious. I'd love to share with you this evening the title of this talk is not meant just to be kind of catchy dance of the fertile universe. First of all, I'm not going to dance, I assure you, because that would make you cry. But the dance of the fertile universe is a very interesting idea. Whoops. See what I told you? Okay, I'll need someone to recover. Is there a laser beam on this? Sorry, Michael.
Oh,
but
no worries, no worries. I don't know if I can. Oh, there you go.
Okay. And the laser beam?
Oh, laser? Who knows? There you go. Yellow.
Oh, that's what I hit. Okay, good. Well, we won't use the laser, I don't think.
There we go.
Could you stay here just a minute?
Sure.
No. That is the laser?
That is the laser.
Okay, we'll not use it.
Okay.
Okay. You'll have to imagine that the laser is going. The dance of the fertile universe has 3 essential, very simple ideas. Okay? It's chance, and necessity, and fertility. And while I'm not going to define them as we go along, I hope you catch the idea of what I mean by each of those. Okay? First of all, I'd like to ask, it's a scientific question. If I walk like this, you can still hear me? Yep. I'm not going to dance, I promise, and I'm not. But I'd like to walk around just in case I'm a moving target. Anyone's going to throw fruit or something. Okay, let's get serious. There is embedded in this scientific question, namely, did the universe and all of us, galaxies, stars, frogs, human beings, okay, come about by chance or by necessity? It all could have happened by chance. That's a distinct possibility. You can't exclude it. But from our scientific knowledge, much less lots of other knowledge, from our scientific knowledge, it's very clear that it's not just chance, and we'll get to that. Did it happen by necessity? That is, was it destined? Is there a purpose to the universe? Okay? So that's a fundamental question. Scientists will never be able to answer the question of purpose, but they can begin to see, is there a design? Is there a structure to the universe that would invite me to think about a being that made it necessary? Consequently, embedded sorry about this, folks. Where do I have to point this to? Embedded in this question, scientific question, is the God question. It's obvious, because if it happened by chance, who needs God? It just happened. If it happened by necessity, who necessitated it? Who brought it about? So later on, I'm going to be a scientist at first, but then this question is embedded in the scientific question, and because it is embedded, we're going to have to address it. Okay? Where do I point this in order to change the... Over here.
Go back.
Why is the universe fertile? For two very fundamental scientific reasons. Facts. We know these facts. The universe is old. 13.8 billion years old. And it contains 10,000 billion stars. Why does that make the universe fertile? First of all, you know what a billion is? 10 to the 9th, 1 with 9 zeros behind it. So 10,000 billion is 1 with 22 zeros behind it, stars. Just so you get an idea. But why does that make the universe fertile? Well, let's first of all get some evidence that we know both the age and the number of stars in the universe. So we start with the Big Bang, and we have very solid evidence that from the Big Bang the universe has been expanding. And this is a slice of the expanding universe. Since the universe is 13.8 billion years old, we are out here at 13.8 billion years since the Big Bang, and we're looking back as far as we can, okay, to the early universe. We've seen back to about 500 million years since the Big Bang with Hubble telescope and other big telescopes. What do we see when we take a picture of the universe back then? That's what we see. We say, what are you so excited about? It's only a bunch of dots of light. Each one of these dots, there are only 4 stars that I can count. Each of those dots is a galaxy. And each of those galaxies contains of the order of 100 billion stars. I'll say in a moment how we know that, but let's sample. I really don't know where to point this to change slides.
There we go.
Okay, it happens by chance. Those circles indicate some sample stars, some sample galaxies that were... That's too far ahead. Sorry about this.
Here. This might...
Yeah, maybe that'll be
just
better.
using those will work better for you, yeah.
Good. Okay, we'll put that aside. That's an irregular galaxy. Contains about half the number of stars in our galaxy. Here is an elliptical galaxy, contains about 10 times the number of stars in our galaxy. By the way, you see that little dot up at the top of that elliptical galaxy? It's a little baby galaxy. And the big elliptical galaxy is eating up the baby galaxy. We call it galactic cannibalism. That's how the big galaxy got big. Not all big galaxies happen that way. But that's not my story. The story is here is a spiral galaxy, which is very similar to our own galaxy. Each of those galaxies contains of the order, some more, some less, but if you assemble them all, the mean is about 100 billion stars in each galaxy. Well, now how many galaxies are there? Well, this photograph was taken of a piece of the sky that's about 1/10 the thickness of my index finger. That's because Hubble telescope wanted to see into the distant universe. It's like I want to see the Empire State Building. I don't know what direction I'm pointing, but let's assume that it's out there. I take a very narrow view because I don't want to see your heads. I want to see the Empire State Building. So that's what Hubble did. It took a very narrow part of the sky. Well, can you begin to get the picture? If this is a sample of the sky, then we do other samples. And we find out that typically the sky is like this. But that's only 1/10 of my index finger, and they're 360 degrees around the sky. So you can easily begin to do the statistics on this, and that's how you come up with 10,000 billion stars. Oh, I can look here. This is a spiral galaxy very much like our own, but it doesn't look like a spiral except for the edges there. But the point I'm trying to make here for this one galaxy, it's very similar to our own, which we're going to look at in a moment, okay, to establish how do we know that, but it measures across 100,000 light years. So if I am at this edge of this galaxy at the bottom right, okay, and my mother-in-law is up there at the top left. I don't have a mother-in-law, I promise you. If I say, Mom, how are you doing? 200,000 years later, she says, oh, son, I'm not feeling so well. I don't enjoy my gin and tonics anymore. No. That is if light travels at the speed of sound, which it does not, but we're going to forget about that. That's not necessary to bring in. So the point I'm trying to make, which is very important, is that we look out in the universe, we're looking back in time. It's obvious, but needs to be repeated. I don't see the folks here in the front row as they are, but as they were a millisecond ago. And the people in back there as they were a millisecond ago. A lot younger. The sun as it was 8 minutes ago. When the sun set, it set 8 minutes ago because it took light from the sun 8 minutes to travel to us. Well, that's very obvious, but we have to bring that to bear because if we astronomers are clever enough, as we look at the similar object at different distances, we're seeing it earlier in the age of the universe. So the very distant galaxies I showed you on that, the expanding universe picture, okay, we're seeing them as they were 12 billion years ago, many of them. Many of them may no longer exist, but the light is just arriving to us. Well, if I take that same type of galaxy and look at a galaxy near us, which is obviously a very old galaxy, okay, then I can begin to, play back how a young galaxy became an older galaxy. So that is a very valuable technique in astronomy to be able to do that. If we turn this galaxy around, okay, by approximately 90 degrees, that is what we would see. we would look down on the galaxy and we'd see the spiral structure. But if we look edge on at that galaxy, that's what we would see. A galaxy is like a tabletop. It's 100 times longer than it is thick. And the sun, as you will see, is out 2/3 of the way to the edge of our galaxy. 100 billion stars spread out over this galaxy. The sun is one of those stars in a universe that contains 100 billion galaxies. That's scientific data. You know, it's not writing poetry, which is great. It's doing science. So what does that say to us as far as the fundamental question we'll get to in a moment? What I want to do is build up from this knowledge of galaxies. I want to build up a picture of how we came to be. I'm going from this immense universe to us. But we have to take it in steps. So first of all, let's take a picture of a little piece of the tabletop of our galaxy. And there it is. That's an actual photograph. And you see an immense number of stars. In fact, this big white area down here in the bottom is not a cloud. It's so many stars packed in that we can't resolve them. Okay? What I'm interested in now, for reasons that will become clear, are the dark areas here. Okay, you see these pockets of dark gas? Why am I interested in those? Well, let's take a little blow-up of one of those dark areas. This is fascinating, always has fascinated me. It's called, for obvious reasons, the North American Nebula. Okay? You can see it. You can see the East Coast. Okay? You can see the Gulf states, Georgia, Alabama, Mississippi. Okay? The Gulf of Mexico, Yucatan Peninsula, the peninsula of Florida. Florida is a little fogged over, but it has been since the elections of 2000. We're not doing a whole lot better, but I'm going to shut up on politics. Why are there so few stars in the Gulf of Mexico and so many stars in the Gulf states? There are not few stars in the Gulf of Mexico. What you sees is not what you gets. If you look in infrared light, this is visible light, and penetrate that gas and dust, you will find a stellar womb. Young stars being born out of that gas and dust. That dark area there, the Gulf of Mexico, is a stellar womb. It's where new stars are being born. How are they born? Well, let's take a look here. This is a Hubble telescope, space telescope photograph of the Orion Nebula, which is a famous constellation, but the nebula is very famous. It's right at the belt of Orion, and it's a star-forming region. And the reason we know that, if you look at this, we blow it up, and you can see that the blue gas and the red gas are more or less separated. There's a little bit of chaotic. Why is that? I mean, you obviously, you look at it and say, that's pretty. You know, that splash of paint. A scientist looks at it and says, oh, it is pretty, but what does it mean? And we know what it means. That area where the red gas is a star-forming region. It's really a stellar womb. And the reason we know it is because the redness of the gas is an indication that the most massive, most energetic stars, which are always the first to be born, the big kids are always born first in this case, because they're more massive. The most energetic are radiating the gas. The gas is absorbing that energy and re-radiating it in the H-alpha line of hydrogen, for you scientists, which is in the red region of the spectrum. So we know from the redness there, and then examining all of it, okay, that that's where young stars, the most massive energetic stars, are formed. Why is the blue gas blue? For the same reason that the sky over St. Louis today and other places, I'm sure, was blue. Because the particles in the Earth's atmosphere are scattering sunlight in the same way that this gas up here, the blue gas, is scattering the starlight from that region there. It's too far from the star-forming region. Nonetheless, it's reflecting that light and scattering it so that the gas is blue. So just the distribution of color here with some careful analysis tells us that we have discovered a star-forming region. So there's a beautiful picture of it in more detail. And you can see the blue and the red are very well separated, and that incandescent gas is really at the heart of this stellar womb. There's a beautiful picture of a piece of one of these dark clouds, okay? Breaking up, those pieces begin to collapse. So take one of those balls of gas there, it collapses. As it collapses, it heats up. Laws of physics, gas physics. As the gas expands, it cools down. As it collapses, it heats up. In this case, this ball of gas is some 4 to 5 times the mass of the sun. So as it collapses, it raises the internal temperature to millions, tens of millions of degrees. In the case of the sun, 15 million degrees. And it starts a thermonuclear furnace. Now that's kind of a big word, but it's a very simple concept. At that very high temperature, the light elements are fused into the heavier elements. Hydrogen, 4 hydrogens combine to form 1 helium. 4 heliums combine to form 1 carbon. You go up the periodic table of the elements. But 1 helium has less mass. I almost was going to say weigh, but you know, I'm a scientist enough not to say weigh. It has less mass than 4 hydrogen atoms. Where the hell did that mass go to? It became energy. E equals mc squared. If you know any equation, you know that one. Einstein's famous equation. So that mass became energy. But it's multiplied by c squared, the velocity of light squared. So a little bit of mass makes a lot of energy. And we have a lot of hydrogen in the sun. It's been doing this for 5 billion years. And it hasn't depleted its hydrogen yet. And it'll do it for another 4.5 billion before it has to begin to convert helium to carbon. So the sun is 5 billion years old. It's got another 4.5 billion. When it goes, of course, even before it goes, we go. But time to go to confession and stuff, don't worry. The essential point here is the following. Each star has a certain mass, so it raises the temperature to a certain level. If it's high enough temperature, it converts hydrogen to helium. When it finishes doing that, it still wants to live, in quotes, so it collapses more, raises the temperature even higher to convert helium to carbon. Because each time you go up the periodic table, it requires a larger temperature, higher temperature, to do the next element. So each star, depending on its mass, will convert lighter elements into heavier elements as it goes through its lifetime. Okay? There is a beautiful example of a cloud breaking up. We estimate we're going to get a cluster of maybe 100, 200 stars out of this breakup of this cloud in the way that I've just said. Well, what is this? It's a dead or dying star. This is the way the sun will die. At the center is a white dwarf. It's a star that collapsed, couldn't raise the temperature high enough, to start a thermonuclear furnace again. So it just collapsed, and blew off its outer atmosphere. It's a dead star. Has no more source of energy other than a little bit of what we call residual gravitational energy. As anything collapses, it forms gravitational energy. It's a dead star. What's this? It's another dead star. But look at the difference between these two. That's a nice, peaceful death, nice swan song. That's the way I'd like to go, just poof. But look at this death, chaotic. It's a supernova explosion. It's a very massive star, okay, because it's so massive, it converted even the heaviest elements all the way up to iron. But when it died a chaotic death. And at the center of it is a neutron star, which is even more massive than a white dwarf. And if you go all the way up, you'll find out that we predicted and have now discovered black holes. But that's another story. Now, why am I talking about the birth and death of stars? Nice story. If this were not happening, you and I would not be here. It's a scientific fact. You know, I'm not trying to pull your leg or anything. If the stars were not, from one generation to the next, generating the chemistry, the heavier elements, we would not have enough carbon, nitrogen, oxygen to form life. This object here in a couple 100 million years will look like this. A supernova remnant. How do I know that? I haven't been around that long. I may look like it. But as I told you before, we look at similar objects at different distances and we can build up a time scale, right? Furthermore, this gas here, we can measure its velocity. Easily done. Routine measurement to measure how fast is it expanding. And we can predict it'll take it a couple 100 million years to look like this. Well, the point is not the time scale, but the fact from this stuff left over from a previous generation of stars, another generation of stars will be born. And so the universe from one generation of the stars is building up ever more heavier elements. At the beginning there was only hydrogen. That's all there was, the simplest element there is. But as stars went on from one generation, we got carbon, nitrogen, silicon, iron, etc., the heavier elements. The sun is a third generation star. And if it were not, you and I would not be here. There would not be enough elements to make life. We are born of stardust. It's literally true. I have a professor friend at the University of Arizona who says we're born of thermonuclear waste. Well, it's true. It's the same reality, but I didn't get as much of a smile when I said thermonuclear waste as I did. Around one star this happened, right? One star in our galaxy developed a planetary system. Now this did not happen by a miracle. We know how this happened. Don't get the idea we know everything about it, but we know how it happened. The laws of physics. This matter left over from the formation of the sun that we just talked about, the collapse of this gas to form the sun, material was left over. But that material had to form into a disk to conserve angular momentum, a basic law of physics. When it formed into a disk, it was much denser. You had a lot more collisions stuck together, built up planetesimals, and finally built up a planetary system. And this little grain of sand came to be. I am allowed to call this a grain of sand. It's one planet among 8 planets, around one star of 100 billion stars, in one galaxy of 100 billion galaxies. So don't get so big-headed about the Earth. Well, it's very precious to us, of course, and should be. And one of the reasons, not even scientists, I think, appreciate enough, one of the reasons it's so precious is this: that through modern science, we have been able to put the universe in our heads. Through physics, math, chemistry, biology, etc. I can tell you what the mass of that galaxy is. I can tell you how fast it's rotating, how many young stars are in it, how many old stars are in it. In us, the universe is reflecting upon itself. I mean, for you old-time philosophers, that's kind of an interesting idea. You know, when I was studying philosophy, you know, the marvel was that we can reflect upon ourselves. We're self-reflecting. In the universe, it's self-reflecting in us. Whether it is in other beings is a whole nother question, you know, whether they're other intelligent beings. Let's leave it to ourselves. This is a marvelous achievement. And when we get that far, we always get more questions than answers. But let's ask a few of the questions. Before I do that, in sort of transiting from the science now to the implications for philosophy and theology, or for us, I'd like to tell a little story. You all knew Holmes, Watson, I think, the famous detective stories that, okay. Well, these two British detectives, okay, are very different characters, but they've worked together all their professional lives, you know? And Holmes is sort of the very kind of, what will I say, philosophical kind of idea, you know? No, it's the opposite around. Holmes is the very empirical kind of idea, and Watson is the big idea guy. They go out on a crime scene, you know, and Holmes picks up little pieces of hair and dust, and they come back to the laboratory. Watson's just looking around thinking, you know, I wonder why he would chop her head off that way rather than that way. You know, he's got these big ideas. They go back to the laboratory, okay? They start talking about this data. Well, they lead very sedentary lives. The only time they get any exercise is going to the crime scene, but they spend most of the time, and since they lead sedentary lives, they get back to they analyze the data for a while, they have a cup of tea, then they have a slow gin fizz and a gin and tonic, and they lead these kind of jolly lives. But one time they have this sudden urge to go on a camping trip. They've never done anything like this. They've never exercised so they go out and to Walmart, you know, and buy all the best equipment. No, they go to a good camping store. They get nice air mattresses, nice backpacks, big 4-man tent. Okay, because being sedentary kind of people, they need a 4-man tent for 2 people. But so they go out camping. They're in Britain. They try and find a mountain, but there are none. But they go up to the top of a hill, and they camp out. They have a nice campfire. First time out, I'm a camper, so I know you have a bottle of wine, nice steaks and all, and for the rest of the trip you're eating this freeze-dried food. But they have a nice meal. They go to bed. And with all this equipment, they still can't sleep very well because they've never slept out. So one wakes up, the other wakes up. At one time, they both wake up together. And they look up, and Holmes looks at Watson, and he says, Watson, what do you think about that? And Watson says, Holmes, it depends on what you mean, what do I think? I mean, they tell me that that is the tabletop of our galaxy, and that there are billions of galaxies. So if you're speaking astronomically, but with all those galaxies out there, there has to be a God if you're speaking theologically. But if you're speaking meteorologically, I got that word out finally, meteorologically, tomorrow we're going to have a great day for hiking and all. Look how clear the sky is. But Holmes, what do you think? And he looks at Watson and he says, "Watson, I think someone has stolen our tent." Thank you. I told that for a purpose. Steal my tent, and I like to steal your tent. We approach this science with prejudicial dispositions, right? Religious beliefs, philosophy, everything.